Alright guys, so today we're going to be looking at the integral test, and I got an example for you from page 618 of the textbook. But before we go about solving this problem, we're going to talk about the pros and cons of the integral test. So essentially you have 10 tests to choose from whenever you're solving a problem about a series, and usually you're given choice about what you want to use. I mean, although there are some problems where you have to use a specific one, like they tell you need to use a specific one, usually you're given a choice. So you do need to know all 10 tests, but sometimes it's better to have 2 or 3 tests that you have as your go-to test. And for me, one of these is the integral test. And that is because the integral test will always give you an answer, and it will always give you an answer that's right. So keep in mind that some of these tests don't always give you an answer. Most of the time they do, but sometimes you'll get an answer that is inconclusive. So for example, if you take the ratio test, if you get a ratio of 1 for the test, then the test is inconclusive. So you have to use another test. And that's just a lot of work. So I don't really want to go there. So I just use the integral test because I know that the integral test will always give me an answer. The second thing is, this test will always give you an answer that is correct. So sometimes, very rarely, but sometimes you'll see that some tests will give you incorrect answers. And that's only usually for unique series. So if you take the harmonic series, for example, the n-term test tells us that the limit as n approaches infinity of 1 over n is 0. So by the n-term test, the harmonic series should converge. But we know that it actually diverges. So this is an example of the n-term test, one test, giving you an answer that is incorrect. But the integral test will always give you an answer that is correct. So those are the pros of the integral test. The cons are you have 3 requirements to check before you can use it, and you have to you have to solve an integral in the test. So now that we've got that out of the way, we're gonna solve this problem. So remember that there are three requirements that you have to check before you can use this test. You have to check to make sure that this function, or the function that corresponds to the series, is positive, continuous, and decreasing for all values whenever x is greater than or equal to 1. And keep in mind that the 1 comes from n equals 1 over here, so if n equals 0, then it's whenever x is greater than or equal to 0. If n equals 2, it's when x is greater than or equal to 2. Usually you'll see 1 or 0, sometimes 2. In this case it's just 1, so we're going to do whenever x is greater than or equal to 1. Now we have to check the first one. So is the function that corresponds to n over n squared plus 1 always positive? Well, first we're going to write out the function that corresponds. It's going to be x over x squared plus 1. Essentially it's just the same thing, but you switch out the x for an n. So is this function always going to be positive? The answer is yes, but you can't just check it off, you have to explain your answer. So let's explain our answer. X is always going to be positive because x is going to be greater than or equal to 1, and x squared plus 1 is always positive. So this fraction will always be positive. So we've checked off the first requirement. Now, is this function continuous whenever x is greater than or equal to 1? Now, usually discontinuities are seen in fractions mostly, and it can be a whole or an asymptote. In this case, we're going to check for an asymptote because there can't be a whole because it's just x in the numerator and you can't factor an x here. So you have to prove that the denominator will never be 0. Because if the denominator is 0, then there's an asymptote, which is a discontinuity. So x squared plus 1 cannot equal 0 because x squared plus 1 can't be negative. And therefore we've checked off this because there are no discontinuities. Now, is this function always decreasing? And for this third requirement, you're always going to want to use the derivative test. You could go through it logically, but it's really the best choice is to use the derivative test because it will give the most thorough explanation and it will always work. So we're going to define this as f of x, and we're going to take f prime of x. So f prime of x is low d high times 1 minus high d low all over the square of what's below. And that's equal to x squared plus 1 minus 2x squared, so negative x squared plus 1 over x squared plus 1 quantity squared. So is this going to be decreasing? And the way you check if f of x is always decreasing is you look at the derivative, and it's good to make a sign study because that in itself will prove that this is always decreasing. So let's make a sign study. Here's our sign study. Sine f prime of x. Okay, so there's going to be a 0 when x is 1 and negative 1, but since we're only looking when x is greater than or equal to 1, we're just going to put 1. And that's the only time there's a 0. But then past that, it's always going to be negative because it's always going to be negative. Whoops. It's always going to be negative. Okay, and this is because the denominator is always going to be positive because it's a squared number, so it's always going to be positive. And the numerator will always be negative because x is greater than or equal to 1, but that doesn't even matter because it's x squared. So basically it's going to be a positive number times a negative number plus 1. And since we're looking whenever x is greater than 1, we already know that this negative number is going to overpower this 1. So this is always going to be negative. So negative over positive is negative. So it's going to be negative whenever x is greater than or equal to 1, and therefore we've proven that this is decreasing because if f prime of x is negative, that means that the behavior of f of x is decreasing. So we've checked off that requirement as well. We checked off all 3, and that took up a lot of work, but now we can solve the test. Now we can use the test. So we have to rewrite this as an integral. So you go from 1 to infinity of the function. And again, keep in mind, the 1 comes from n equals 1, so if it's n equals 2, you use a 2. And don't forget the dx, because that's an easy way to lose points. And now let's solve the integral. This one's pretty simple, because it's going to be a natural log, because you can recognize that the top is 1/2 of the derivative of the bottom. So if you take out a 1/2, you have 2x over x squared plus 1 from 1 to infinity dx. And that is the limit as b approaches infinity of 1/2. You can take out the 1/2 if you want. I'm just going to include it because it looks better in my opinion. Of natural log of x squared plus 1 from 1 to b. And I use b because this is an improper integral because it goes to infinity. But you'll get the same answer if you don't. It's just, this is the proper notation. So now that we have this, we're going to solve. So it's going to be 1/2 the natural log, the limit as b approaches infinity. The natural log of b squared plus 1 over 2 minus the natural log of 2 over 2. And the natural log of b itself is going to be infinity, so the natural log of b squared plus 1 is going to be definitely infinity. So we have infinity essentially. You don't have to even look at this number because it's going to be a constant, so it's just going to be infinity. And what this tells us is that the integral diverges, and therefore the series diverges. So remember, whatever happens to the integral happens to the series. So we've proven that the integral diverges, and therefore we can prove that the series has diverged. And that is the integral test.